Welcome to Approach to ABG's Part 7, Multiple OSIS Processes. We're going to take a look and see what happens when you have multiple OSIS processes and then give a few numerical examples. So, can bicarb and CO2 both change at the same time? Yes, they absolutely can. And we're going to take a look at what happens when both of them have changed. How does this influence the shifting of the equation to the left or to the right? Remember again, bicarb, the normal value is 24, and the normal value for CO2 is 40. And the bicarb processes we call metabolic, and the carbon dioxide processes we call respiratory. When you have two OSIS processes at the same time, there are 4 combinations. You could have respiratory acidosis with metabolic acidosis, respiratory acidosis with metabolic alkalosis, respiratory alkalosis with metabolic acidosis, and respiratory alkalosis with metabolic alkalosis. So 4 different combinations, and we're going to take a look and see what happens to the shifting chemistry for each of these 4 combinations. Remember, you want to determine the OSIS before you determine the emia. All right, so if we have a bicarb that is elevated, that's going to shift the equation to the right. This is going to consume hydrogen ions, and we expect the hydrogen ion concentration to go down. Now, at the same time, if the CO2 is reduced, what's that going to do? That's going to create a little vacuum on the right side of the equation, so it's going to also shift right. And this is going to consume hydrogen ions. So now we have 2 OSIS processes that are both alkalosis. We have a metabolic alkalosis because the bicarb is elevated, and we have a respiratory alkalosis because the CO2 is reduced. When this happens together, we always produce alkalemia because both processes are moving in the same direction. What about when the bicarb is elevated? So that's going to be a metabolic alkalosis. It's going to shift the equation to the right, reduce hydrogen ions, and at the same time we have CO2 that's elevated. That's going to push the equation to shift in the opposite direction, which is going to increase hydrogen ion concentration. So here we have a metabolic alkalosis process. We have a respiratory acidosis process. And I haven't told you what the numbers are, so we can't know which of these processes is bigger. The bigger one is going to push the pH in that direction. But if they're both the same size, they can neutralize each other, and you might have a completely neutral pH. You could have a pH of 7.40, so there's no acidemia, there's no alkalemia, but we have 2 different OSIS processes. And this is why you have to look at the change in bicarb and the change in the PCO2 before you look at the pH, because the pH could be normal, and if you just looked at the pH and saw a normal pH and said, oh, everything is normal, you would make a mistake. Let's take another look at another example. Here we have a low bicarb. This is going to create a little vacuum on the left side, shift left, hydrogen ions go up. And if the PCO2 was elevated, this is also going to push the equation to the left. Hydrogen ions will go up. Here we have a metabolic acidosis process, a respiratory acidosis process, and because they are both acidosis processes, they will always produce acidemia. So here's a double metabolic and respiratory acidosis. Our fourth example, we've got a drop in bicarb. So that's going to give us a shift to the left. It creates a little vacuum on the left. Hydrogen ions go up. And we have a drop in the PCO2. That's going to create a little vacuum on the right. It's going to shift to the right, and that's going to drop the hydrogen ion concentration. So this is very similar to the second example where we have opposing processes. We have a metabolic acidosis and a respiratory alkalosis. We haven't told you which one is bigger, so it could create acidemia, alkalemia, or if they're both the same magnitude, it could create a normal pH. So let's do some numbers, and we're going to do the same analysis as we just did, except now we've got numbers for everything. So a pH of 7.18, a PCO2 of 50, and a bicarb of 18. These are the normal values for your reference. We're going to analyze the PCO2 first. So PCO2 of 50 is elevated. That's going to shift the equation to the left, give us some more hydrogen ions. Bicarb is reduced. That's going to create a little vacuum, shift to the left, and more hydrogen ions. So this is going to give us, this is going to give us a double acidosis. We have a metabolic acidosis and we have a respiratory acidosis, and they have created together an acidemia. We have a pH that is less than 7.40. Second example, pH 7.40. Look at that. It's normal. PCO2 of 30, reduced, and a bicarb of 18, also reduced. Let's analyze the PCO2 first. It's reduced. This is going to create a little vacuum on the right side. It's going to drop the hydrogen. The bicarb is low at 18. That creates a little vacuum on the left side. That's going to shift it back, and it's going to increase the hydrogen. So now we have an example where we have a metabolic acidosis process and a respiratory alkalosis process, but we don't have acidemia, we don't have alkalemia, we actually have a perfectly normal pH. So this can happen. Third example, pH 7.32, PCO2 60, bicarb 30. PCO2 is elevated, that's going to push things to the left and increase the hydrogen. Bicarb is elevated, that's going to push it back and decrease the hydrogen. And when we sort of step back and take a look, we can say, all right, we've got a metabolic alkalosis process. We have a respiratory acidosis process, and we have acidemia. The pH is less than 7.35. Remember, the normal range is 7.35 to 7.45. So here we can just look at it and we can say, the respiratory acidosis is bigger than the metabolic alkalosis because we ended up with acidemia. Third example, pH 7.47, PCO2 60, bicarb 42. Let's analyze this. So first things first, CO2, it's elevated, shift left, more hydrogen ions. Bicarb, also elevated, that's going to shift it back. It's going to drop the pH, and we've got a metabolic alkalosis process. We have a respiratory acidosis process, and the final pH is alkalemia. So we know that the metabolic alkalosis process is bigger than the respiratory acidosis process. So, key details. Look at the pH last. Look at the CO2 and the bicarb first to determine. You might have 0 OSIS processes. That would be fairly a normal blood gas. Maybe you have 1 OSIS process or 2 OSIS processes, which is what we just looked at. And if you have a metabolic and respiratory OSIS at the same time, they can be in the same direction or opposing directions in how they influence the pH. And if they are both a metabolic and respiratory OSIS, sometimes they can cancel each other out and create a normal pH.